Welcome to this coding problem walkthrough. In this session, we will dive into problem number 330, titled Patching Array. We'll explore the problem statement, analyze potential approaches, and ultimately arrive at an optimal solution. Let's get started. In this problem, we are given a sorted array of positive integers called nums and a target range, 1, n. Our goal is to ensure that any number within this range can be formed by the sum of some subset of the elements in the array. To achieve this, we are allowed to patch the array by adding the minimum number of additional numbers. The task is to return the count of these patches. For instance, if the given array is 1, 3, and n is 6, we need to determine how many numbers we need to add to make all numbers between 1 and 6 formable using subsets of the array. Let's explore the input and output format. The input consists of the sorted array nums and the integer n, while the output is a single integer representing the minimum number of patches needed. Now, let's dive into some examples to understand this better. In the first example, the input array is 1, 3, and n is 6. The output is 1, which means we need to add one patch to achieve the goal. Initially, the array 1, 3 allows us to form sums 1, 3, 4, but some numbers in the range 1, 6 are still missing, namely 2, 5, and 6. To bridge this gap, we add the number 2 to the array. After patching, the array becomes 1, 3, 2, and we can now form all numbers in the range 1, 6 using subsets of this new array. For example, 1 is already present, 2 is the patch, 3 is in the original array, 4 can be formed as 1 plus 3, 5 is 2 plus 3, and 6 is 1 plus 2 plus 3. Thus, the minimum number of patches needed is 1. In the second example, the input array is 1, 5, 10, and n is 20. The output is 2, indicating that 2 patches are required. Initially, the sums we can form with 1, 5, 10 are 1, 5, 6, 10, 11, 15, 16, but there are many missing numbers in the range 1, 20. Specifically, numbers like 2, 3, 4, 7, 8, 9, and others cannot be formed. To address this, we add the numbers 2 and 4 to the array. After patching, the new array becomes 1, 5, 10, 2, 4, and this allows us to form all sums up to 20. For instance, 2 is now directly in the array, 3 can be formed as 1 plus 2, 4 is a patch, 7 is 3 plus 4, and so on. By adding just 2 numbers, we bridge all the gaps, so the minimum number of patches required is 2. In the third example, the input array is empty, and n is 7. The output is 3, which means we need to add 3 patches. Since the array is empty, no sums can initially be formed, so we start by adding the smallest number, 1. Next, we add 2, which allows us to cover a larger range of sums, and finally, we add 4. With these 3 patches, the array becomes 1, 2, 4, and now we can form all numbers in the range 1, 7. For example, 1 is the first patch, 2 is the second, 3 is 1 plus 2, 4 is the third patch, 5 is 1 plus 4, 6 is 2 plus 4, and 7 is 1 plus 2 plus 4. Thus, to cover the entire range, the minimum number of patches required is 3. There are some key constraints and edge cases to consider. First, the value of n can be as large as 10 to the power of 9, so the solution must be efficient. Adding numbers greedily or iteratively is often more practical than trying to calculate all possible sums directly. Next, if the input array nums is empty, we need to start patching from 1 and continue until the range 1 n is fully covered. On the other hand, if nums already covers all numbers in 1 n, no patches are needed. Finally, when nums contains sparse elements that are far apart, multiple patches may be required to fill in the gaps. These considerations highlight the importance of understanding the structure of the input array and the target range to develop an optimal solution. To begin, let's consider the brute force approach. The idea here is to generate all possible subsets of the given array nums and calculate their sums. Once we have these sums, we can identify any missing numbers in the range 1, n, and repeatedly add those numbers to the array until the entire range can be formed. While this approach is guaranteed to work, it's computationally expensive. Generating all subset sums has an exponential time complexity, making it impractical for larger inputs. Specifically, the time complexity is 2 to the power of m*n, where m is the size of the array and n is the upper bound. Additionally, it requires 2 to the power of m space to store the subsets. Because of this high computational and memory cost, the brute force approach is not feasible for larger inputs, and so we reject it in favor of more efficient methods. Now, let's turn to the optimized greedy approach. Here, the focus shifts away from generating subsets to targeting the smallest number that cannot currently be formed. We start with miss equals 1, which represents the smallest missing number in the range, 1n. Using this, we iterate through the array. If the current number in nums is greater than miss, we patch the array by adding miss and then update miss by doubling it. On the other hand, if the current number in nums is less than or equal to miss, we use it to extend the range of numbers that can be formed and move on to the next element. This process continues until miss exceeds n. The key insights here are that miss always represents the smallest unformable number, and adding miss doubles the range of formable numbers. By focusing on this smallest number and patching only when necessary, we minimize the number of patches required. The algorithm involves initializing miss, an index pointer, and a patch counter, then iterating through the array while making decisions based on the value of miss. The time complexity is m plus p, where m is the size of the array and p is the number of patches, with p being at most logarithmic in n. This makes the approach both time efficient and space efficient, using only constant space. We chose the greedy approach because it's efficient, scalable, and guarantees the minimum number of patches. It aligns well with the problem's requirements and is straightforward to implement. While exploring alternatives, we also considered a binary search approach. This method uses binary search to find the largest number in nums that does not exceed miss at each step. If no such number exists, we patch the array with miss. Although this eliminates the need for a linear scan, it introduces additional complexity due to the binary search operations. The time complexity here is p log m, where p is the number of patches and m is the size of the array. While effective in some cases, this method has slightly higher complexity and is less practical, especially for smaller arrays where the linear scan of the greedy approach is already efficient. For these reasons, we prioritize the optimized greedy approach. Ultimately, we selected the optimized greedy approach as our chosen strategy. Its simplicity, efficiency, and scalability make it the ideal solution for this problem. By focusing on the smallest missing number, miss, at each step, we either extend the range of formable numbers using elements from nums or patch the array to cover the gap. Each patch doubles the range of numbers that can be formed, ensuring that we solve the problem with the fewest possible patches. This approach is not only computationally efficient, with minimal overhead, but also optimal in terms of the number of patches required. Compared to the brute force and binary search methods, the greedy approach stands out for its practicality and ease of implementation, making it the most effective and accessible solution for this problem. In this problem, we need to ensure that every number in the range from 1 to n can be represented as the sum of some subset of an input array called nums. The challenge is to do this while adding the minimum number of additional integers to the array. To understand the approach, consider this key insight. At any point, if the current array can form all numbers up to some value x, then the next missing number is x plus 1. To cover this gap, we would need to add x plus 1 to the array. To implement this idea, we start by initializing a variable miss to 1, which tracks the smallest number that cannot currently be formed. We also use an index to iterate over the sorted array nums, and a counter, additions, to keep track of how many numbers we add. With this setup, we can systematically address the gaps in coverage using an efficient, step-by-step process. The first step in the algorithm is to sort the input array nums in ascending order. This is important because it allows us to process the elements sequentially, ensuring we maximize the range of numbers covered with the elements already in the array. Once sorted, the core of the algorithm involves iterating through the array while ensuring that all numbers up to n are covered. If the current element in nums is less than or equal to miss, we include it in the range by adding its value to miss, effectively extending our coverage. We then move to the next element in the array. However, if the current element is greater than miss or we've exhausted all elements in nums, it means there's a gap in the coverage. To close this gap, we add miss itself to the array, increment the additions counter, and update miss to double its previous value. This doubling effect ensures that the range of numbers we can form grows exponentially, allowing us to efficiently close gaps. The process continues until miss exceeds n, at which point all numbers in the range, 1 each n, are guaranteed to be covered. Finally, the algorithm returns the additions counter, which represents the minimum numbers added. The key insight in this algorithm is the greedy choice to always add the smallest missing number, miss, to the array. This is the most efficient way to minimize the number of additions while maximizing the range of numbers that can be formed. Each time we add miss, the range of numbers we can cover doubles, because every previous sum can now be extended by adding this new value. This doubling effect is what makes the algorithm highly efficient. The process stops once miss exceeds n, as this means all numbers from 1 to n are now covered. To support this strategy, we use a sorted array to ensure that elements are processed in ascending order, and we track progress using simple variables like miss, index, and additions. In terms of complexity, sorting the array takes O, k log k, where k is the size of nums. The iteration and additions take O, k plus m, where m is the number of additions made. Therefore, the overall time complexity is O, k log k, and the space complexity is O, 1, as no additional data structures are required beyond the input array and the variables. There are several edge cases to consider in this problem. First, if the input array nums is empty, the algorithm will add numbers in the sequence 1, 2, 4, 8, and so on until the entire range from 1 to n is covered. This is because miss starts at 1 and doubles with each addition, filling the gaps efficiently. Second, if there are large gaps between elements in the array, the algorithm handles this by adding miss directly to close each gap as it iterates. This minimizes redundant additions and ensures coverage is expanded systematically. Finally, if the input array already provides complete coverage for the range, 1 n, no additional numbers are needed, and the result is simply 0. These edge cases highlight the robustness of the algorithm, which adapts dynamically to the structure of the input array and ensures the solution is both efficient and correct. This code solves the patching array problem by determining the minimum number of patches, integers, required to ensure the input array can represent all numbers in the range, 1 en, through subset sums. The function min_patches starts by initializing three variables: patches to track the number of patches added, max_reachable to represent the maximum sum we can reach with the current array, and I for iterating through the array. Inside the while loop, the condition max_reachable n ensures that we continue patching until the entire range, 1 n, is covered. For each iteration, we check if the current number in the array, nums, I, is less than or equal to max_reachable plus 1. If it is, this number extends the range of reachable sums, so we update max_reachable and move to the next number in the array by incrementing I. If the current number in the array is too large, or if we've exhausted the array, we add a patch. The patch is chosen as max_reachable plus 1, which is the smallest number that can extend the range of reachable sums. We increment patches and update max_reachable accordingly. This approach ensures that we efficiently cover the range, 1 en, while minimizing the number of patches. The algorithm has a time complexity of O, m, where m is the length of the input array, as we iterate through the array and only perform a constant amount of work per iteration. The space complexity is O, 1, since no additional data structures are used. This is the Java implementation of LeetCode problem number 330, patching array. The logic mirrors the provided Python implementation, with differences such as explicit type declarations and the use of long for handling larger sums. The function calculates the minimum patches needed to cover the range, 1 en, using a greedy approach, where the max reachable variable tracks the maximum sum reachable so far. Here, we start with the example where nums is 1, 3, and n is 6. Our goal is to make sure that all integers from 1 to 6 can be formed by using the numbers in nums and potentially adding some patches. Initially, the patches count is 0, the maximum reachable sum is 0, and the index I is 0. In the first iteration, max_reachable is 0, and nums, 0, is 1. Since nums, 0, is less than or equal to max_reachable plus 1, we can use this number to extend our range. By adding 1 to max_reachable, the value becomes 1, and we increment I to 1. In the second iteration, max_reachable is now 1, and nums, 1, is 3. However, nums, 1, is greater than max_reachable plus 1, so we cannot directly use it yet. Instead, we add a patch equal to max_reachable plus 1, which is 2. This increases the patches count to 1, and max_reachable becomes 3. Now we have extended the range to cover up to 3. Continuing with the next iteration, max_reachable is now 3, and nums, 1, which is 3, is less than or equal to max_reachable plus 1. This means we can use nums, 1, to extend the range further. Adding 3 to max_reachable gives us a new value of 6, and we increment I to 2. At this point, max_reachable has reached 6, which is equal to n. Therefore, we terminate the loop. The final result for this example is that we needed one patch to ensure all numbers from 1 to 6 could be formed. Now, let's look at another example where nums is 1, 5, 10, and n is 20. Again, we aim to cover all numbers from 1 to 20. Initially, patches is 0, max_reachable is 0, and I is 0. In the first iteration, max_reachable is 0, and nums, 0, is 1. Since nums, 0, is less than or equal to max_reachable plus 1, we can use it to extend max_reachable. Adding 1 to max_reachable updates its value to 1, and we increment I to 1. In the second iteration, max_reachable is now 1, and nums, 1, is 5. Since nums, 1, is greater than max_reachable plus 1, we cannot use it directly. Instead, we add a patch of max_reachable plus 1, which is 2. This increases patches to 1, and max_reachable becomes 3. Next, max_reachable is 3, and nums, 1, which is 5, is still greater than max_reachable plus 1. So, we add another patch of max_reachable plus 1, which is 4. This brings the patches count to 2, and max_reachable is updated to 7. Now, nums, 1, is less than or equal to max_reachable plus 1, so we use it to extend the range. Adding 5 to max_reachable gives a new value of 12, and we increment I to 2. In the fifth iteration, max_reachable is 12, and nums, 2, is 10. Since nums, 2, is less than or equal to max_reachable plus 1, we use it to extend max_reachable further. Adding 10 results in a max_reachable of 22, and I becomes 3. At this point, max_reachable is greater than or equal to n, so we terminate the loop. The final result here is that 2 patches were added to cover all numbers from 1 to 20. In this example, nums is empty, and n is 7. With no initial numbers, we need to form all integers from 1 to 7 using only patches. Initially, patches is 0, max_reachable is 0, and I is 0. In the first iteration, max_reachable is 0, and since nums is empty, we add a patch of max_reachable plus 1, which is 1. This increases patches to 1, and max_reachable becomes 1. In the second iteration, max_reachable is now 1, and again, we add a patch of max_reachable plus 1, which is 2. This brings the patches count to 2, and max_reachable becomes 3. Finally, max_reachable is 3, and we add another patch of max_reachable plus 1, which is 4. This updates patches to 3, and max_reachable becomes 7. At this point, max_reachable is equal to n, so we terminate the loop. The final result for this example is that 3 patches were necessary to cover all numbers from 1 to 7. The time complexity of the algorithm can be understood by analyzing the 2 key operations it performs. First, it iterates through the input array nums. For every element in nums, if the element is less than or equal to max_reachable plus 1, it gets used to extend the max_reachable value. This step processes each element in nums at most once, which makes it run in linear time, or len nums. The second operation involves adding patches. Whenever an element in nums is not suitable to extend max_reachable, the algorithm adds a patch, which is simply the value max_reachable plus 1. This patch effectively doubles the range of max_reachable in constant time for each patch added. Since max_reachable doubles with every patch, the number of patches needed to span the range, 1 to n, is proportional to the logarithm of n, specifically O log n. Thus, the time complexity of adding patches depends logarithmically on n. In scenarios where the input array nums is empty or contains very few elements that are widely spaced, the algorithm has to rely heavily on adding patches to achieve full coverage of the range, 1 is n. In these cases, the time complexity is dominated by the number of patches, which is O log n. Combining this with the time spent iterating through nums, the overall time complexity of the algorithm is O len nums plus log en. Now turning to the space complexity, the algorithm requires only a few scalar variables to operate: patches to keep track of the number of patches added, max_reachable to track the current maximum range covered, and I as an index pointer to iterate through nums. Since these variables are fixed in number and do not depend on the size of the input, the space complexity remains constant at O(1). When compared to a naive or brute force approach, the efficiency of this algorithm becomes even more apparent. A brute force method would involve testing all possible subsets of nums, including patches, to determine the smallest set that can cover the range, 1 en. Each time a patch is added, the algorithm would need to recalculate reachable ranges, leading to an exponential time complexity of O(2) nums in the worst case. In contrast, the greedy approach ensures that we add the smallest possible patch, max_reachable plus 1, at each step, which maximizes the range extended per operation. This makes the algorithm computationally efficient, reducing the time complexity to O len nums plus log n. In terms of best and worst cases, the algorithm performs optimally when nums already covers 1 n, requiring no patches and simply iterating through nums in O len nums. In the worst case, where nums is empty or insufficient, the algorithm must add patches until the range is fully covered, resulting in the combined time complexity of O len nums plus log n. The logarithmic dependence on n can also be understood mathematically. Every patch operation doubles the value of max_reachable, starting from an initial value of 0. To reach or exceed the target value n, the number of patch operations required is at most log_2 n. This doubling behavior ensures that the patches grow exponentially, minimizing the total number of operations. When we add the linear time required to process the input array nums, the total time complexity becomes the sum of these two components, O len nums plus log en. This combination of linear and logarithmic growth ensures that the algorithm remains efficient even for large values of n and sparse input arrays. Here, we're looking at some of the most common mistakes when solving the patching array problem. First, misunderstanding the problem scope is a frequent issue. It's essential to fully grasp the goal, like knowing which subsets or ranges need to be formed. If you overlook these requirements, your solution might miss critical cases, leading to errors or wasted time during implementation. Next, an inefficient brute force implementation is another common pitfall. Trying to naively calculate all subsets for large arrays, especially when the size exceeds 20, results in exponential time complexity. This is computationally infeasible for larger constraints, such as when n equals 10,000. Another frequent mistake is off-by-one errors in handling the range, 1 en, such as forgetting whether n is inclusive. This can cause numbers to be skipped or overcounted, leading to incorrect results. Finally, neglecting edge cases like an empty array or a single-element array often breaks the solution's logic, causing runtime errors or incorrect outputs. Testing these edge cases is critical to ensuring your implementation works in all scenarios. Overcomplicating the solution is another mistake to watch out for. Adding unnecessary checks or extra loops can make your code more complex without improving its performance. This not only increases the chances of introducing logical errors but also makes debugging more challenging. Now, when it comes to interviews, there are a few key insights to keep in mind. First, understanding subset formation is crucial. Many problems in this category revolve around forming all possible sums using subsets, and recognizing this early can simplify your approach significantly. Greedy strategies are often the best choice for these problems, as they allow you to iteratively eliminate gaps in the range by adding the smallest missing number. Additionally, always tailor your solution to the problem's constraints. For example, if the input size is large, prioritize algorithms with O n or O n log n complexity. Finally, be prepared to explain your decisions. For instance, you might need to justify why a greedy approach is more suitable than dynamic programming, focusing on trade-offs like time complexity and implementation simplicity. There are also related problems that you can study to deepen your understanding of the patching array problem. For instance, LeetCode 322, the coin change problem, also involves forming sums using a set of numbers. Similarly, LeetCode 39, combination sum, and LeetCode 40, combination sum 2, focus on generating combinations to achieve specific sums, with the latter adding the constraint that elements can only be used once. Another useful problem is LeetCode 860, lemonade change, which applies a greedy algorithm to handle constraints incrementally. Now, when considering alternative approaches, dynamic programming is a viable option. By using a DP array to track possible sums, this method guarantees correctness but comes at the cost of higher space complexity, typically O(n). Sorting combined with a greedy strategy is another alternative. By sorting the input array, you can iteratively check whether each number can form the next required sum. While sorting adds O(n) log n complexity, this approach is straightforward and easy to implement. Finally, there's backtracking, which explicitly generates subsets and verifies sums. However, this method has exponential time complexity, making it suitable only for small input sizes. Each approach has its trade-offs, and understanding these will help you choose the best one for your specific needs. Great job completing this problem. We reviewed the patching array problem, discussed key approaches, and highlighted important takeaways. Remember to keep practicing similar problems to strengthen your problem-solving skills. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!